You've got the basics of C++ down. This video covers 5 Level 2 lessons that turn you into someone who can design real classes, write generic code, pick the right container, manage memory safely, and handle errors like a professional. We'll go lesson by lesson, in the order they build on each other, pulling real code straight off the page. Stick around to the end for links to every lesson we cover. First up, Object-Oriented Programming, the deep dive version. Inheritance, virtual dispatch, abstract interfaces, and 2 traps that catch nearly every C++ programmer at least once. Dog inherits publicly from animal. A dog really is an animal. The derived constructor must build the animal part first, in its initializer list. And notice name is protected, not private, so dog's own methods can reach it directly. Area is virtual, so calling it through a shape reference correctly dispatches to circle's version at runtime. Describe isn't virtual, so you get the generic base version even on a real circle. Mark anything you intend to override virtual, and add override so the compiler double-checks you. That equals 0 makes area pure virtual, and that makes shape abstract. You can never create a bare shape, only a rectangle or circle that implements every pure virtual. Storing them means a vector of unique pointers to shape, never a vector of shape by value. Pass a derived object into a function that takes a base by value, and it gets sliced. Only the base part survives, and you lose the override. The fix is simple, always pass polymorphic types by reference or pointer, never by value. The second trap, delete a derived object through a base pointer, and if base's destructor isn't virtual, only the base part gets cleaned up. Its own destructor never runs, and anything it owns leaks silently. Any class with a virtual function needs a virtual destructor too. That's the object model, done right. Next up, we make code work across types entirely, without writing it twice. Templates. Templates let you write one function or class that works for int, double, string, or anything else. The compiler generates the specific version you actually use. Call maximum with 2 ints, and the compiler deduces t as int and instantiates an int version on the spot. Call it with 2 doubles, and you get a completely separate double version automatically, no extra code from you. A class template works the same way, just for a whole class. Stack of int and stack of string share the exact same source code but are completely unrelated types. Once instantiated, you can't assign one to the other. Templates can take values too, not just types. Fixed buffer of double, 4 and fixed buffer of double, 8 become genuinely different types, with the size baked in at compile time. This is exactly how std array gets 0 overhead. Sometimes one type needs genuinely different logic. A full specialization gives bool its own describe function, printing yes or no instead of the number 1 or 0 that to_ string would give you. The compiler prefers the specialization whenever the type matches exactly. Here's the single most common beginner template bug, putting the class declaration in a header but the method bodies in a separate CPP file. It compiles, then fails at link time, because the compiler never sees the actual code where stack of int gets used. Template definitions belong in the header, always. With generic code sorted, let's put it to work. The standard libraries containers, and when to reach for which one. Now the containers themselves. The honest rule most engineers skip, use vector unless you have a measured reason not to, and here's why that's true. Plus the traps in map and hash tables. Vector is contiguous memory, so a plain scan over it is cache-friendly and usually beats a linked list in practice, even though list insertion is theoretically faster. Reach for deque when you need to push at both ends cheaply, and list only when you're inserting constantly in the middle. Size is how many elements you have, capacity is how many fit before vector needs to grow. When it grows, it reallocates, and every pointer, reference, and iterator into the old memory instantly becomes dangling. If you know roughly how many items are coming, call reserve up front. Maps operator bracket is convenient for counters, but it has a hidden side effect. Reading a key that doesn't exist actually inserts it, default valued. Just checking if ages of nobody equals 0 silently adds nobody to your map. Use at, find, or count when you only want to look, not insert. Unordered _ map trades that sorted order for speed average constant time lookup, by hashing the key instead of comparing it. If you need sorted iteration or range queries, stick with map. If you just need the fastest possible lookup by key, unordered _ map is almost always the better default. Stack, queue, and priority _ queue aren't full containers, they're adapters that wrap something like deque and restrict you to one interface, last in first out, or always grab the biggest. Notice pop returns nothing, you call top first, then pop, so a throwing copy can never lose an element. Pick the wrong container and you pay for it in performance. Pick the wrong ownership model and you pay for it in crashes, which is exactly what smart pointers fix next. Manual new and delete is exactly how memory leaks happen: one early return or one thrown exception, and your cleanup code never runs. Smart pointers fix that by tying the lifetime of memory to the lifetime of an object. Here's the classic bug: allocate an array, and if the function throws before reaching delete array, that memory is gone forever, leaked, with no way back. Adding try-catch around every allocation is exhausting, and easy to forget even once. Unique _ PTR owns its object exclusively. Copying one is a compile error, on purpose, so there's never a question of who's responsible for deleting it. When it goes out of scope, the destructor runs automatically, and it costs nothing extra over a raw pointer. Shared _ PTR allows real shared ownership. Each copy bumps an atomic reference count, and the object dies only when the last owner does. That safety costs something real: atomic updates and a bigger pointer, so reach for unique _ PTR first, and shared _ PTR only when ownership is genuinely shared. Two nodes that shared _ PTR each other create a cycle: neither reference count ever hits 0, and both leak silently, forever. The fix is weak _ PTR, an observer that doesn't affect the count. Owners hold shared _ PTR downward, observers hold weak _ PTR upward. 2 hard rules to memorize: never build 2 smart pointers from the same raw pointer, that's a double delete waiting to happen. And get returns a non-owning raw pointer for legacy APIs, never delete it yourself, the smart pointer already will. Memory that manages itself is half the safety story. The other half is what happens when things go wrong at runtime: exceptions, and how to handle them without making things worse. Last stop: making failures survivable. Custom exception types, cleanup that can't be skipped, and the judgment call of when an exception is the right tool at all. Deriving your own exception from std runtime _error is the pragmatic move. You pass your message to the base constructor and inherit a correct, safe what function for free. Validation error also stores the field name directly, so callers can react programmatically instead of parsing an error string. Group-related errors under a common base, so callers can catch at whatever level of detail they need. Order matters: catch handlers top to bottom, most specific first, generic std, exception last. And always catch by const reference. Catching by value slices a derived exception, just like the object slicing from Module 1. C++ has no finally, and it doesn't need one. When an exception propagates, every local object's destructor still runs during stack unwinding, in reverse order, so a smart pointer frees its memory, and a file stream closes itself, even on the unhappy path. One hard rule: never let a destructor throw. If an exception is already unwinding the stack and a destructor throws a second one, the runtime calls terminate and your program dies instantly. No handler gets a chance to run. If cleanup can fail, give it an explicit close or commit method instead. And the judgment call: exceptions are for exceptional situations, not routine control flow. A user typing letters instead of numbers is normal, expected input model that with a return value, like std, optional, and save throwing for things the caller genuinely can't recover from. That's the arc: solid objects, generic code, the right container, safe ownership, and errors you can actually recover from. Everything you need to write C++ that holds up in production. If you want to run any of this yourself, every lesson is linked below, in the order we covered them: OOP, templates, STL containers, smart pointers, and exception handling. Thanks for watching, and see you in Level 3.